Hello and welcome to what will be for many people watching this video, their introduction to further maths A-level content. And believe me, we've got a lot of really cool maths to show you, and what better way to do this than to start with an interesting topic such as complex numbers. To begin with, let's give a little background by taking a look at solving quadratics, which is hopefully a topic you're already familiar with. You're also hopefully familiar with by now the idea that quadratics appear to have different numbers of roots, depending on which quadratic you're looking at. For instance, this quadratic, we can see how many roots it has by calculating what's known as the discriminant. The discriminant for this quadratic would be equal to minus 4 all squared, minus 4 times by 1 times by 5. And that comes to minus 4. And because minus 4 is less than 0, that tells us that this particular quadratic has no real roots, because the discriminant is the part of the quadratic formula that lies under the square root sign, and as we all know, we can't take the square root of a negative number, or so we might think. You see, we do have to be really careful with our wording when we talk about the numbers of roots of a quadratic. You see, I didn't just say the quadratic had no roots at all, I was very careful to say that it had no real roots. And the reason that's important is because that word real has a meaning in maths. We have something known as real numbers, which is a set of numbers sometimes represented by this weird looking R notation that you can see on the screen right now. But what are real numbers? Well, put simply, they're all the sort of numbers you've ever come across before in Maths A-level or Maths GCSE up until now. They are all the positive numbers, the negative numbers, the decimals, the fractions, the rational numbers, the irrational numbers like pi, square root of 2, etc, etc. All the numbers that you've come to know and use that lie on the traditional number line. But are these actually all the numbers? Well, not really, and it's because of the fact that real numbers are just called real numbers because they're numbers that are easy for us to represent as quantities in the real world. Any real number could represent a certain amount of something. The trouble is, by defining numbers in that particular way, you're putting restrictions on what you're calling a number, and therefore you're also putting restrictions on the types of calculations you can do. And the thing is, that is a bad idea to do in maths because it's shutting off whole possibilities, and this is a concept you've actually already come across earlier in your education. If you rewind to when you were first doing counting, you might have learnt how to count objects, like for instance, you could have pencils on a table, and if you're just counting things in that way, you're only interested in whole numbers, 1 pencil, 2 pencil, so on and so forth. It doesn't make sense in that context to be thinking about something such as fractions. Whether you have half a pencil or a third of a pencil, it doesn't really matter that much in what you're doing there. But then later you would have progressed into doing calculations that required knowledge of fractions. For instance, measurements involving units of time. You could have years being split into smaller fractions as months, months being split into days, days being split into hours, and so on and so forth. Each of these things can be expressed as fractions of another thing. The problem is, if you started doing calculations with those things, but limited yourself to only being able to work with whole quantities of those things, then some of the accuracy to your calculations would be lost as a result. For instance, let's say you're talking about days and you had 1.4 days, add 1.2 days, plus 1.3 days, plus 1.1 day. Of course, if you just added these all up officially in their decimal format, including all those parts of a day added on, that would mean in total you would have 5 days. Whereas if you were somebody who only believed in whole amounts of these things, you'd probably end up only doing 1 plus 1 plus 1 plus 1, which would give you a different number. And it's important to therefore be aware that although these small little things appeared insignificant when counting whole numbers of days, when combined together, they can then combine to be something important again. And it's the same idea that we're going to be using now, because it'd be very easy to stay in the world of real numbers and only believe those are the only things that exist. But the problem is, in doing so, we're ignoring a portion of a calculation that could, after some accumulation, become something very, very important indeed. And it's at this point of the story we introduce the idea of imaginary numbers. Because just like if we restrict ourselves to only dealing with whole numbers and ignore fractions, we're missing out on a whole area of maths and lots of different calculations. Similarly, if we only stick to real numbers, we're also restricting ourselves from being able to do some maths that we would really like to be able to do. For instance, with real numbers, as we already mentioned, you can't take the square root of a negative number. Whereas we can now define the square root of -1 as the number I, which is what we call an imaginary number. We call an imaginary number purely in the sense that it's not a number we can picture with our eyes in the world around us. But that doesn't mean it doesn't exist, and the more calculations you do with these things, the more important you start to see they become. Imaginary numbers can then be combined with real numbers to make what we call complex numbers, where a complex number is a number that's got both a real part, in this case the number 5 is our real part, and then an imaginary part, which in this case is the 8 lots of I that we have over there. We then have official mathematical notation to help us refer to the set of all the complex numbers, which is this fancy looking C that you can see on the screen right now. But just to make it clear, the set of all complex numbers includes all the real numbers, all the imaginary numbers, and all the numbers made up of a combination of real and imaginary numbers. Okay, so that's a few definitions out the way, but let's start doing some calculations because that's the fun bit of maths. For instance, we could be trying to solve this quadratic, and if we were only dealing with real numbers, this is a quadratic for which we'd say there was no real roots. But now we're allowed to do calculations involving imaginary and complex numbers. Well, actually, we can find some solutions to this equation. It's worth mentioning that until now, X has often been the go-to letter to write in equations that you're trying to solve. But you'll notice in this equation, we've got the letter Z, and that's actually not insignificant. You'll start to see more equations that do this, and it's because sometimes when they write that, they're trying to give you a hint that it's not only real numbers that are possible values for solutions to the equation, but now complex numbers are a possibility as well. So let's get started. If we're trying to solve a quadratic, well, technically there is a way we could factorize it, but factorizing starts to become something you don't really want to do so much with complex numbers. So instead, what you're going to want to do is use the trusty old quadratic formula, because the solution to this equation will just be z equals minus b, which in this case would be therefore minus 6, plus or minus the square root of b squared, so minus 6 all squared, minus 4 times by 1 times by 13. And that's all being square rooted, of course. And on the bottom, we're going to be divided by 2 lots of a, which in this case is 2 lots of 1. We can then go ahead and start trying to calculate what this would be. We're of course going to get a 6, we're going to get a 36 inside the square root, and minus 52 from there, which is interesting because it means, surprise, surprise, we've got a negative number inside the square root. We've got minus 16 inside there. That's interesting because it means we can now use index laws to split up this third. The minus 16 inside the square root could be rewritten as the square root of 16 times by the square root of minus 1. And the reason we like to do that is because now we can rewrite this as 6 plus or minus 4 lots of I, because the square root of minus 1 is I. We're still dividing by 2, and that means therefore overall the roots of this equation are 3 plus or minus 2i, and therefore we've found solutions to this equation. They're complex, but they are still solutions. And while we're introducing things, I may as well point out various other things that you can do with complex numbers. For instance, we can add and subtract them, and that works exactly how you'd expect it. Because I is written a bit like an algebra letter, then we can combine complex numbers by adding them just like you would add algebra. You'd end up adding the constant terms together just as separate numbers, and then we'd also separately add the bits with the i's in together as well. So therefore we're going to end up doing 5 plus 6, which is 11, and 9 plus minus 2i, which comes to plus 7i. We can also subtract them, and it's just like subtracting algebra, you've got to multiply out the brackets effectively. So we've got 8 plus I minus 15 minus 9i, which is of course plus 9i, and that means we've got in total 8 minus 15, which is minus 7, and I plus 9i, which is 10i. Something else interesting happens when we start taking powers of imaginary numbers. For instance, we know that I is the square root of minus 1, but therefore we can calculate what I squared is, because I squared would just be effectively undoing the square root that appeared in what I was representing. So therefore I squared is just going to be minus 1. But therefore we can also calculate I cubed, because that would just secretly be I squared times by I, which would just be minus 1 times by I, so I cubed is just minus 1 lots of I. And then I to the power of 4, well, you could view that lots of different ways. You could either view it as I cubed times by I, or you could even view it as I squared all squared, but however you choose to view it, you're going to end up getting positive 1. So you see, this is why complex numbers are interesting. Although individually they might seem weird and something that doesn't matter in the real world, the thing is they can be combined in certain ways again to reach real values, and that is why they are so important. What we've just looked at could be viewed as a repeating pattern though, because if you wanted to calculate any higher powers of I, well, we can just continue this pattern on. For instance, I to the power of 5 would just be looping back round to the beginning again, because it would just be I to the power of 4 times by I, which is then just going to be one lot of I, so just I. And that means we can take this idea to the extreme. What happens if you want to do I to the power of 203? Well, the thing to be aware of there is the number 200 is a number that's a multiple of 4, and it's the last multiple of 4 below the number 203. So therefore we can rewrite this as I to the power of 200 times by I to the power of 3. As I to the power of 200 is to the power of a multiple of 4, then therefore that means that we've got actually a quite nice number appearing there, which is just ultimately the number 1, because 1 to the power of anything is just 1. And because I cubed was just minus I, that means I to the power of 203 is just minus I, even though it had that really mega crazy power. That's pretty cool. And the reason this is interesting is because it opens up the door for us to be able to do other things, such as multiplying complex numbers together, because guess what? It acts exactly how you expect it to by just multiplying out the brackets, like with algebra. So, for instance, we do 5 times by 6, which is 30. We can do 9i times by 6, which is 54i. We can do 5 times by minus 2i, which is minus 10i. And then if we've got 9i times by minus 2i, that's going to be minus 18i squared. Now that minus 18i squared can be rewritten as a different number, but I still like to rewrite it out as minus 18i squared, just like it's algebra first, because, let's face it, the further you go into maths, it's not the harder concepts that start to trip you up after a while, it's the really basic numerical stuff like adding and taking away and dealing with minus signs appropriately. And that's why we've got to be careful here, and why I'd still recommend writing out minus 18i squared first, because then it forces you to take a second to stop and think and go, oh yeah, of course, I remember I squared is secretly minus 1. So therefore we've got to be careful, because we have minus 18 lots of minus 1, which means we've got a minus minus situation. So the 30 is going to be combined with a positive 18 to get 48. And then of course we've got the 54i minus 10i, which leaves us with 44i. So there you go, those are some things we can do with complex numbers, but trust me, this is just the beginning of the story, and there's loads of really cool stuff we've still got to look at with complex numbers. And just as a little side note before we go, it's worth mentioning that the format we've been using for complex numbers today is sometimes called Cartesian form. But hopefully you found today's video useful, and hopefully I'll see you in a future video for more stuff with complex numbers. Goodbye.